So I'm going to present a little bit of an overview of the work I've been involved in during the last years, and that deals mostly about the North Atlantic. We've had a couple of workshops, and when I was at Durham University working with Iceland-Faroes, so everyone can probably imagine that has been a lot of fun. I want to also say special thanks to Kenny Pedersen, one of my best colleagues, who has unfortunately left academia, but he's done a lot of work with me, and a lot of this, what I'm going to present, is his work. So just to mention that. So you know the title, so I'll just get going. So if we look at the North Atlantic, most of you have probably, or it's the Northeast Atlantic, most of you know that region, maybe more or less degree. What we can see is an oceanic spreading system with many complexities. And in the center of it is Iceland, or the Greenland Iceland-Faroes ridge, with high bathymetry compared to the neighboring ocean basins. And this will be the center of my talk, even though I'll be also talking about general rifting and passive margin formation. But this is more like we were trying to find a generalized model for the North Atlantic. And I think we've come quite far. We've produced a lot of ideas, but these now need to be tested in the next, 10, 20 years, I guess. So anyway, if we look at Iceland and the Greenland Iceland-Faroes ridge, it has high topography bathymetry. It is covered by various kinds of volcanic rocks, which makes this actually a little bit problematic to see what it actually is. Is it anomalous oceanic crust, or is there maybe something else underneath? So because of this volcanic extrusive cover, it is very difficult to for example, see isochrons if they are there. So you can see exactly here this corridor of very different magnetic anomalies compared to the very nice ones usually in the neighboring ocean basins, and this makes it just difficult to really distinguish whether this is oceanic crust or something else. In this compilation over here, these isochrons have been deleted where they are very diffuse or not very well to identify. But at the same time, we can, or not, I haven't done this, but other people from this publication have actually identified rift systems in the Greenland Iceland-Faroes ridge. And these have actually different ages. So the rift systems are jumping around. There's no real systematic to it as far as I understand. So this is a jumping rift system along this ridge, which is also quite interesting. From a geophysical point of view, Iceland is also very special because this map is showing the geophysical data set as of 2003, and it is not really straightforward to characterize Iceland geophysically because it is very unlike anything else we know. It has actually quite thick crust. It can have thick crust, but a large part of it is high velocity lower crust of not really known composition. So this is very odd, and that's why this expression Iceland type crust has been developed, because it is not continental really, It is not really oceanic, it is something else. And we're trying to find out what it could be, of course. These are studies from receiver functions, of different age and different data sets, different methodologies, showing the MOVO depth. And I mean, there are some similarities as always. And what is really the highlight, I think, here is that all of these are showing that there is crust thicker than 40 kilometers, or at least 35 kilometers. And some compilations, or I think these are actually gravity density models using a priori data from seismic constraints to really illustrate this. So there is this ridge with enormously thick crusts, possibly up to 45 kilometers, which is very, very unusual. And this, I'm not going to talk very much about it, but this is accompanied by quite anomalous geochemistry. So there's water in the basalts and glasses on Iceland, and the amplitudes of what's that called? Concentration of water is actually increasing towards Iceland. And there are also hints for continental contamination. I will leave it to that because I'm not really a geochemist. So this led already early on to models proposing that Iceland might be partly underlain by continental crust. Then I will come to my PhD work, which I really like to mention because this really got me interested in the North Atlantic. And as it turned out later on, it was actually quite helpful when, if our hypothesis is right, which it probably is not, but this can be actually quite a good, it's a central piece in this hypothesis. So what we see here is a receiver function common conversion point image. I won't go into the details, but red colors mean that you have a downward increasing velocity. Blue means the downward decreasing velocity, and that forms a high velocity layer. And we thought, or we interpreted this as eclogitized crust, lower crust, or oceanic crust perhaps also, subducted in some subduction event. And we modeled this using several methods, and this is how the synthetics look like up here, and the observed receiver functions, and we think it's quite a good match. And where does this come from? Of course, an obvious candidate could be the Caledonian orogeny, but also perhaps earlier events, but this is not what this talk is about. The important thing is it's there, and we then furthermore try to correlate it to the fan reflector on the other side of the North Atlantic, north of Scotland. And they have quite a similar geometric shape, and if we look at receiver functions, they have also quite an okay match in the receiver function signature. The data I used here are very poor in that there are unfortunately no better data around so far. But this really convinced us that this might have been the one and the same structure. And if you actually just draw a line between them, this might be really an essential part in understanding Iceland and young Mayan. Okay, I'll get on with some numerical modeling, and that's with Kenny Peterson from Aarhus. And what we want to know is what happens if we extend this system, such a fossil subduction zone with possibly eclogite and maybe even serpentinite in there. And what our main aim was can we actually produce high velocity lower crustal bodies with these pre-existing materials? And we could to some degree, and this might actually explain some of the high velocity lower crust we can see in passive margin. But what is actually also very interesting is that just by playing around with the crustal thickness and thereby the total crustal heat production and thereby the crustal temperatures, we could let the crust become warmer or colder. In case of a warmer crust, we got crustal flow, so the crust could extend much more, and at the same time we could extrude volcanics on top of it. So it was actually producing volcanic margins when we had a thick crust and a warmer crust. This can of course also be produced or modeled in a different way, but the most important thing is the warm crust. Yeah, and vice versa, a cold crust would have produced non-volcanic margins. We took this a little bit further and really tried to model this a bit bigger and on a regional scale. And in this case, we tried, this is unfortunately only 2D, we never managed to actually do it in 3D, but it should really be done at some point. We produced, or we built, a very, very simplified orogeny with thickened crusts here and underlain by a high density lower crust. And this is metastable unless you actually perturb the system. So once you start rifting, a lot happens. So the whole lithosphere actually delaminates. You get crust in contact with the asthenosphere, which means the crust becomes very, very weak. And as you can see here in the last sketch, the whole rift system is filled with flowing crust. Now, this is of course an end member model. It's probably very unlikely to happen, but why not? I mean, to some degree, it might as well happen. So, so that's actually quite interesting. Here's a zoom, so you can see that we have asthenosphere all the way up here, the blue-gray stuff. Here's some melt, and we have flowing, extending crust all over the rift system and overlain by volcanics, because all this gray stuff has molten before, has melted before. So hot crust is really the key here. And we try to do this for specifically for the North Atlantic. I don't know if this video will work, so I'll do my best. So now you can see, I don't know, maybe 100 million years of quiescence. This system is metastable, although there's high density lower crust in here. And once you start perturbing the system, a lot happens. The lithosphere delaminates, cross-cuts the mantle transition zone, and it produces actually a plume coming from the lower mantle and producing a lot of magmatism. Yeah, and we kind of try to turn the buttons and push the knobs so that we get the right timing for the North Atlantic. And this is our melting curve, the background, the kind of nervous, spiky curve. And on top of that are the melting curves extracted from refraction seismic models. And the timing and the amplitudes are actually quite all right. So we are happy about it. Yeah, I will skip this one. So the conceptual model is that we've had a lot of pre-existing structures. We had orogens, we had the Caledonites, of course. We also had the, sorry if I pronounce it wrongly, but the Tectonic orogeny crossing or coming across Greenland and into Scotland. And I will mention this again on the next slide. This will be my last slide. But anyway, we are rifting here, and we are crossing the, let's say, the Caledonites with a potentially, or with a definitely thick crust, potentially eclogitized remnants in there. And we are rifting, and at some point it becomes unstable, and we delaminate the lithosphere. That means asthenosphere is rising to the lower crust, the lower crust becomes very, very weak and is able to flow into a channel, which may be the Greenland Iceland-Faroe ridge. So,
sorry to interrupt, Christian, but you reached the 50 minutes as well.
Okay, good. I'm also done now. So the conceptual model is basically that we are moving the crust. The crust is flowing into this channel, and why exactly there? Perhaps because it's the western front of the Caledonites, but perhaps also because it's the northern end of the Tectonic orogeny. And actually something very similar happens in Davis Strait, where we also have the NGS, the NAGS orogeny. So we think this could be actually a feasible model for the Northeast Atlantic. We need to further explore this, this connection over here to Davis Strait. But otherwise, there's a lot of work to do, and this is really just a conceptual model based on reviews we did and ideas we got during these workshops. So that's it. Thanks for listening. Yes.
Thank you, Christian. We have time for 1 or 2 quick questions. Anybody wants to start? I guess it's up to me to have at least one. In your model, where you had everything layered, and then only when something happened in the lithosphere, you got the plume from the lower mantle. That's very interesting to see. I was wondering how realistic this initial condition is, that everything is so quiet and laterally homogeneous and nothing is happening. In real world, you would expect much more dynamics before the onset of actually something happening in the lithosphere. How would you see this and the impact of this dynamics in the beginning?
Yeah, that's a big problem, I would say, because of course we are not in 2D, we are not 3D, we don't have a 1D or almost one-dimensional world. We also had rifting in the North Atlantic since the Jurassic or even Devonian. I mean, this system has not been that stable, which is a bit of a problem for this model. But we are looking here at kind of end members, so it depends on what weights, what negative buoyancy this lower crust, this dense lower crust would have. If it was thinner and the lithosphere stronger, it might as well be more stable till more severe rifting happens. So, of course, there are many factors and that play into this. Even if you have such a oversimplified setup, there are still an infinite amount of factors you can change, which will make your model work or break down. But yeah, of course, it's it is what we have to deal with, I guess.
Okay.
Yeah.